Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis, taken by Professor Krishna P. Kaliappan. Myself, Sri Lakshmi S. I am a fourth year PhD scholar in IIT Bombay. So, in the last tutorial sessions, we have discussed several questions regarding this topic which were taught in this course, and we have discussed the lecture content as well. So, in today's lecture, we will be first discussing the week 2 assignment questions, then we will move ahead with the week 3 lectures. No, week 3 lectures we have already discussed, so first we will discuss some questions for this. One second. Yeah, so first we will discuss the week 2 assignment question, then we will move ahead with the contents of some lectures, that was week 4 lectures. Then we will see some questions related to the week 4 lecture topics. So firstly we will start with the week 2 assignment question. So the first question of week 2 assignment was, what is the correct sequence of steps followed to get the product obtained in the reactions given below? So the first option So the first option is photochemical followed by photochemical reaction and thermal reaction. Option B is 4 plus 2 cycloaddition followed by 2 plus 2 cycloaddition and FVP. Then 2 plus 2 cycloaddition followed by 4 plus 2 cycloaddition and FVP. And last option is 4 plus 2 cycloaddition followed by FVP and 2 plus 2 cycloaddition. So out of these four options given here, which will be the correct answer? So we have already seen this question in the lecture video as well, where a series of cycloaddition reaction is happening in this. So please find the correct option given here. So here what is happening is that first, upon treating this cyclopentadiene with this benzoquinone fragment, a Diels-Alder reaction will happen where this fragment act as the diene and this act as the dienophile to get this compound. Then what is happening? This can be redrawn as this one. So first step is 4 plus 2 cycloaddition. Then second step is 2 plus 2 cycloaddition. So if we redraw this structure into this form, this is a 2 pi electron system, this is a 2 pi electron system, so this 2 plus 2 cycloaddition will happen in the presence of H nu to form this compound. So that will be the correct answer, 4 plus 2 cycloaddition followed by 2 plus 2 cycloaddition and FVP. So this particular dione which is given here is known as Cooksen's dione. So cyclopentadiene act as the diene and benzoquinone act as the dienophile. Under heating condition, it will undergo this 4 plus 2 cycloaddition reaction. And here, if we redraw like this, the double bonds are close enough to undergo photochemically 2 plus 2 cycloaddition to get this Cooksen's dione. The next question is the correct match for the structures of prostaglandins in column 1 with their names in column 2. So here column 1 is the structures of different prostaglandin. In column 2 we have to find each of the structure is corresponding to which type of prostaglandin according to the four options given here. So here, as we have discussed, the PG in this name of prostaglandin stands for prostaglandins. So PGA, PGB, PGC means all have cyclopentene, but the double bond position will be different. Now PGD and PGE is having no double bond but ketone and beta hydroxyl group. PGF is having two hydroxyl groups in cyclopentene. So considering all these factors, which will be the correct option here? So here the correct answer is option A. So the first structure corresponds to PGF. As I told, it will be having two hydroxyl group in cyclopentane, and the second one corresponds to PGE because there is no double bond and ketone and beta hydroxyl group is there. Then the option C corresponds to PGA, and because if it is double bond is coming here, it will be PGA. If it is coming at this position, it will be PGB, and if it is coming between this R alpha and R omega, it will be PGC. So the last one will be PGC. I hope it's clear about the naming of prostaglandins. Now the next question, identify the correct transformation. Ignore the numbering of the question. Identify the correct transformation taking place in the reaction given below. So this is an electrocyclization reaction. It is clear from the question. Now it is which electrocyclization reaction? Conrotatory 6-pi electrocyclization, disrotatory 8-pi electrocyclization, conrotatory 8-pi electrocyclization, or disrotatory 6-pi electrocyclization. So about this conrotation and disrotation, what is the role 6 pi 8 pi systems we have seen in the lecture video as well and in the last tutorial session as well. So which will be the correct answer here? So here, as we have discussed earlier, this is an example for con-rotatory 8 pi electrocyclization. So here con-rotation means this will shift to here and this will rotate to here and the cyclization will happen, and as we can see, both of these groups will be in the opposite phase because this is rotating here and this is coming here, so this will go below and this will come above. So this is an example for con-rotatory 8 pi electrocyclization. Now the next question, identify the correct order of reagents used in the following transformation. So here a reaction is given. So this is the transformation, as we can see this OH is getting converted into OTBDPS. But the options given here are option A TBDPSCl imidazole DCM 0 degree Celsius. Option B first iodine K2CO3, then second TBDPSCl and base, third zinc dust and acetic acid. Third option is TBDPSCl N-butyl lithium minus 78 degrees Celsius. Last option is first zinc dust acetic acid, second TBDPSCl and base, third one K2 iodine and K2CO3. So which will be the correct answer here? So here the correct answer is iodine K2CO3, then TBDPSCl and base, then zinc dust and acetic acid. So here is a reason why we are not directly treating it with TBDPSCl imidazole, because there is a selectivity issue between the two primary hydroxyl groups present here. So directly treating with TBDPSCl imidazole DCM condition can give directly this dye substituted product. So that's why here it is followed in a sequential manner. So So what will happen here is, first in the presence of iodine K2CO3, one of this hydroxyl group, that this hydroxyl group is only undergoing this Appel reaction to come iodine here, and then treating with TPDPSCl base, there is no selectivity issue. So instead of this OH, their OTPDPS will come, then zinc dust acetic acid to convert that iodine back into the hydroxyl group will give this product. So the correct answer is option B. Now the next question, the major product formed in the following reaction. So here when this particular compound is subjected for photochemical condition or exposed to light, what will be the product? So here what is happening is that this is a kind of carbenoid mediated reaction. So think in that way and try to find the answer. So here what is happening is that first in the presence of light, so here a negative charge will be formed and that will attack at this position and N2 will be living, so that will result in 1, 2, 3, 4. A beta lactam formation will be resulting. So this is one of the method for generating a beta lactam via a carbenoid intermediate. Now, the fifth question, identify A in the following reaction. So, this A, upon treatment with KOH, we are getting this cubane carboxylic acid derivative. So, which starting material we have to start with to get this compound? So here we have already seen a quasi-Favorsky reagent of one of the starting materials will result in this product, and the correct answer is option C. So we have seen that where we are starting with this halogen in the starting material, in the product the carboxylic acid will be coming in exactly the same position as that of the bromine. So here, since carboxylic acid is in this position, we will have to start with the option C to get this corresponding product. So as we have seen the mechanism, so here if this is the starting material, this OH minus will attack at this ketone carbon, and this bond will migrate to here and bromine will leave to get this derivative. So this is used for the synthesis of cubane. Now the next question, identify the reaction taking place in the reaction given below. First one is conrotatory 6 pi electrocyclization. Second one is disrotatory 8 pi electrocyclization. Third one is conrotatory 8 pi electrocyclization. And last one is disrotatory 6 pi electrocyclization. So which will be the correct answer here? So here, this is the product of the, just before some time we saw a question, this was the product of that reaction. So here again it is undergoing an electrocyclization. So which will be the product? So this ring is undergoing electrocyclization as it is evident from the product, this ring. So identify the product here. So here the correct answer for this question is disrotatory 6-pi electrocyclization. So this compound will undergo disrotatory electrocyclization. So this electrocyclization is happening. So this will come here, this will go here, and this will go here, and we will get this cis hydrogen stereochemistry, which is endiandric acid F. Now the next question, identify the major product A and B in the following reaction. So this compound upon treatment with NaOH and H2O, we will get a compound A, which upon further treatment with this potassium iodide, sodium bicarbonate and water, we will get a compound B. So we have to identify the correct options for this compound A as well as compound B. So here what is happening is that in the first NaOH H2O hydrolysis condition, this uh, lactone hydrolysis will happen and the ring will open to get this compound, that is this open compound. Then in the presence of Ki and sodium bicarbonate, this iodonium ion will form and it will open up to form this iodide compound. So that iodine will be coming in, the iodonium ion will be coming in the opposite phase of this carboxylic, this like whatever this alkyl chain. So the correct answer will be option D. So first step is that lactone ring opening, that is hydrolysis we can say, and then iodonium ion formation, and that iodonium ion will open up to give this answer D. Now, the next question, identify A in the following reaction. So, this compound A, upon treatment with this PCl3, we are getting this lactam ring, beta lactam ring. So, which will be the corresponding starting material we have to use to get this product? So here the correct answer is this one, option C. So here also what is happening is that this one, 2, 3, 4, this nitrogen lone pairs will attack over this center. Firstly, in the presence of PCl3, this acid will be converted into corresponding chloride, and this nitrogen lone pair will attack over here, and the Cl minus will leave out to get this beta lactam ring. Now, the next question, identify the major product A in the following reaction. So, this compound upon treatment with toluene in one heating at 1 to 30 degrees Celsius, which will be the major product formed here. So, here as we have seen, this is a type of Diels-Alder reaction, and because of this ester group, there will be secondary orbital interaction, and this will be the major product here, where this TBDPS, this CH2-TBDPS, and this ester group will be having opposite stereochemistry, and this ester will be in cis configuration with this two protons in the junction position. So that was the last question of week 2 assignment. I will give you some time to go through all the questions, and if you have any doubt, please do let me know. Then we will move ahead with the discussion. So that's all about the week 2 assignment. Now we will move ahead with the discussion on the week 4 week 4 lecture contents. So the first lecture was about triquinanes by radical cyclization reaction, where we have seen the total synthesis of the sulfy ferfolene and modipheine, which is a propellant type of compound. This sulfipherfolone is an angular triquinane, which is given here. So it involves the repositioning of a side chain on the cyclization template to get the angular triquinane by extension of tandem radical cyclization strategy. And in the synthesis of sulfipherforyl by Curran's group, the key reactions were 5 exoteric radical cyclization, where they used 3-ethoxy 2 cyclopentenone as the starting material. And we have also seen they have utilized Wolff-Kishner reduction. And this total synthesis was completed in 1987 in 7 linear steps and 6.4 percentage overall. Now, for the synthesis of this modipheine, which is isolated from the golden rod plant, and it is known for its toxicity to cattle and sheep. So, it contains a 333 propylene carbon framework. And the principal problems of this total synthesis are there are three contiguous quaternary centers. So, this one, two, and this three. And the control of relative stereochemistry at the stereo center bearing a methyl group will be also difficult. And the architecture of propylene ring system does not permit tandem radical cyclization, but it should be done in stepwise manner. So here they synthesized this modifying starting from cyclopentene 1,3 dione using this Ireland Clayson rearrangement, radical cyclization by using catalytic tributyl hydride, catalytic AIBN, and equivalent amount of sodium cyanoborohydride. Then they have also utilized Negishi coupling, and this synthesis demonstrates the utility of fragmentation method for achieving high yield and high stereo selectivity in intramolecular 5-exocyclization. And they have achieved this total synthesis in 14 steps and completed it in 18 percentage overall yield. So here we have seen this Wolff-Kishner reduction. So that is basically the conversion of this carbonyl compound into its corresponding alkane derivative. So by using this hydrazine, water, KOH, and heating condition. So what's happening here is first this treating this carbonyl compound with this hydrazine and elimination of water molecule will result in the formation of this kind of compound hydrazone. Then again OH minus will take this proton of this NH2 to form this NH minus, and then this negative charge will come over here and this will come over here to form this negative charge, which is quenched by this proton of this KOH to get this compound. Again then OH minus will come here and take this proton to uh, this electrons will shift to here and this bond will break, N2 will eliminate and H2O will eliminate to form this. Again KOH will protonate this to form this compound. So that's how in Wolff-Kishner reduction this ketone is converted into corresponding alkane by using hydrazine and a base. Now the next lecture was about triquinanes by photochemical reaction. No, in the lecture 16 itself we have seen the Ireland Claisen rearrangement. So here it is a kind of 3 3 sigma tropic rearrangement where we have already seen the mechanism before also. So here what is happening is that this compound, this protonation, deprotonation will take place from the alpha position of this ester. So it will give this enolate anion, and this negative charge will attack over the silyl chloride silicon and it will form this enol TMS. Then once this enol TMS is formed, then OH minus will attack over the silicon and this bond will shift to here to form this intermediate. Then an H plus it will get protonated to form this, and water molecule will leave and it will form this carboxylic acid. So that is the mechanism for this Ireland Claisen rearrangement. So here we can see a 3 3 sigma tropic rearrangement is happening. So this, if we take as 1 2 3 and this is 1 2 3, a bond is forming between 3 3 position and it is breaking between 1 and 1 position. So Ireland Claisen rearrangement is a type of 3 3 sigma tropic rearrangement. Then we have seen this Negishi cross coupling reaction in the lecture 17. So that is basically a palladium or nickel catalyst coupling reaction between an organozinc compound, zinc halide, and an alkyl halide. So basically it is a type of coupling reaction. So if we see here, this zinc compound will undergo coupling with this aryl halide to form this compound. So this mechanism is very clear to us. It can undergo coupling with this also, so it will give this compound. So the mechanism is first oxidative addition of this aryl halide or this halide to this palladium will give this compound. Then transmetallation will take place with the zinc complex to eliminate SN2, and this will be forming. Then cis trans isomerism will happen so that this R group and this R dash group will come cis to each other. Then reductive elimination of that R dash, the coupled product will lead to the formation of the catalyst back. So that is the mechanism of Negishi coupling reaction. Now, in the next lecture, we have seen this triquinanes by photochemical reaction by Demuth and Uehara, where we have seen the application of oxidipymethane rearrangement and photochemical 1,3-acyl shift in the total synthesis of sulfipherfol and capnylane. So, Demuth synthesis of sulfipherfol 1651 in 1988. A tricyclic enone was obtained from chiral enone via Diels-Alder methodology, and the key reaction was oxidipymethane rearrangement. Starting material used in the synthesis was hagosparish ketone and hagosparish ketone, which could be obtained from 2-methyl cyclopentane 1,3-dione and methyl-vinyl ketone. So then we have seen what is oxidipymethane rearrangement, and if 1,3-acyl shift is taking place, butanone will result in the oxidipymethane rearrangement rather than cyclopropane. Then we have also seen what is Robinson annulation, and they completed this total synthesis in 11 linear steps with 1.6 percentage of overall yield. This we will come. Yeah, and then in Uehara's total synthesis of Capnylane, we have seen a photochemical 1,3-acyl shift in a bicyclo 3,2,1 octixene 2-on derivative for generating dicunane unit of capnylane, and the starting material used was metacresol methyl ether, and the synthetic equivalent which of for ketene they used was alpha chloroacylonitrile, and the key reactions involved were Sujitro's reaction, Birch reduction, Diels-Alder reaction to get the bicyclic ketone, and they completed this total synthesis in 13 linear steps with 3.7 percentage of overall yield. So now we will see the mechanism of the reaction which we saw. So this is Robinson annulation reaction. This we have already seen about hagosparish ketone. So this methyl cyclopentane 1,3-dione and methyl vinyl ketone RT 5 days. This Michael addition will happen to give this product. So that mechanism is given here. First with the esprolin, this it will form the iminium ion kind of derivative. Then that elimination will give this Michael addition product, and then in the presence of this esprolin again an aldol type of reaction is happening, and that aldol reaction will give this bicyclic hydroxydione. So then PTSA mediated or in heating condition this OH will eliminate, and here double bond will come, so that is hagosparish ketone. So depending on the catalyst we are using here, whether we are using esprolin or the other derivative, we can change the stereochemistry of this methyl center. Now, the oxidipymethane rearrangement is this compound when we are treating with photochemical condition, a cyclopropane ring is forming. So, how it is happening? This first, this O radical will form, and here also one radical is forming. So, this here also radical will form. This two will combine to form this compound. Then this O radical will come here, and this bond will break to form this C radical and this C radical, which can combine to form another cyclopropane ring. So if it is coming like this and this radical is forming, then this two can combine to form this epoxide as well. Mostly this cyclopropane ring will be the product in oxidipymethane rearrangement. So these are the some of the examples for this oxidipymethane rearrangement. Here also you can try to find the mechanism for this reaction, which is same, exactly same as the previous conditions which we previous mechanism which we saw. So this O radical will form here and this C radical will form and the cyclopropane ring. Then again this O radical will come here. This bond will break to form this radical which will combine to form this cyclopropane ring. And this will not be happening. This epoxide formation is not favored. The cyclopropane ring formation will be favored. Now this Sujitros reaction, so here in the presence of this palladium catalyst, this allyl group will eliminate and one nucleophile is coming over that center, that is known as Sujitros reaction. So what is happening first, this allyl halide will undergo oxidative addition, or this palladium can coordinate with this allylic group to get this compound, and this X will leave and it will undergo oxidative addition on this palladium to get this compound. Then again this palladium can either come to this position or this position, and depending on that, in the other position nucleophile will be attacking to get this compound. So this is known as Sujitros cellulation. Now in the next lecture, we have seen the triquinanes by photochemical reaction, application of TMS iodide mediated rearrangement of and arene olefin meta photocycloaddition in total synthesis of hierostine and ceratopicanol by Oda, Bender and Shannon's group. So in Oda's total synthesis, we have seen they have synthesized hierostine by a TMS iodide mediated rearrangement, where it is a short and elegant synthesis of plus or minus hierostine in 4 steps. And this was done by 1986 with an overall yield of 36% and 4 linear steps, where they used the starting material cyclohex 2 in 1,4 diol. And in Oda's total synthesis of capnellane, and this capnellane was isolated in 1978 by Gerasi from soft coral Capnella imbricata. And the key steps involved in that reaction involved titanium mediated ester ketone reductive coupling as key reaction, and they completed it in 6 steps. So the key reaction in that capnellane total synthesis was McMurray coupling. And they use starting material cyclohex 2 in 1,4 dione by Diels-Alder reaction, then the reduction of double bond followed by retro-Diels-Alder by pyrolysis, then 2 plus 2. So they used a series of cycloaddition reaction, TMS iodide mediated rearrangement, and the first total synthesis of capnellane was reported in 1987. They completed it in 6 linear steps with 25% of overall. Then in Vender's synthesis of isocoamine, We have seen the arene photocycloaddition, and they have used starting materials like 2-bromotoluene, methylvinyl ketene, and ketone and bromobutane. Then Channon's total synthesis of the ceratopic enol. We have seen an intramolecular irene olefin metaphotocycloaddition as the key step, and they have done this in 1996 using 7 steps and 19.2 percentage of overall. And in Wender's total synthesis of subergorgic acid, which is given here, which is an angular thiocyanine, we have seen the benzylic ketyl assisted stereo controlled intramolecular irene olefin metaphotocycloaddition, and the starting materials used was 2-bromo 1,4-dimethyl benzene. They completed this total synthesis in 1990 using 11 linear steps and 15 percentage of overall. So here we have seen this McMurray coupling, which is titanium mediated coupling reaction between this ketone. So it will form this titanium intermediate like this. Then this will combine to form this intermediate, and then this TiO2 will lead to form this alkene. So that is known as McMurray coupling. So here is a detailed mechanism which is same as that we saw here. Titanium dioxide will leave and alkene will be the major product. Then the lecture 19 was about the trichonanes by thermal metathesis, where we have seen the applications of photothermal metathesis reaction and intramolecular Michael addition reaction in the total synthesis of histidine and deoxymagnellaninone by Mehta group. So there we have seen the synthesis of tricyclic sesquiterpene hydrocarbon, which is plus or minus histidine, involving a novel photothermal metathetic sequence as key step to generate linearly fused tricyclopentanoid framework by Mehta's group in 1981, and they have used cyclopentadiene as the starting material. So this is the thermal metathesis reaction, a 4 plus 2 cycloaddition reaction between this cyclopentadiene and benzoquinone will give this compound. Then 2 plus 2 photochemical cycloaddition reaction intramolecular to will give this Cooksen's diol, which upon pyrolysis, that was FVP, flash vacuum pyrolysis, will give this to retro 2 plus 2 to get this linear triconane core structure in 3 steps. So here the atom economy of the reaction is 100%, and this formal total synthesis was first reported in 12 longest linear sequence and 13.1 percentage of overall yield. Then this Mehta's total synthesis of deoxymagnellaninone, which is having a two 5-membered rings, one 6-membered ring, and one N-methyl piperidine. Then it will undergo a thermal metathesis and intramolecular Michael addition methodology and Walker process to get the methyl ketone. And that total synthesis was completed in 1990 using cyclopentadiene and benzoquinone as the starting materials, and they completed it in 11 linear steps with 2.03 percentage of overall yield. Then the ceratopicanol was isolated in 1988. As we can see from the structure, it is having 5 contiguous stereogenic centers on a cis anti-cis triconane framework. And the first total synthesis in 1991 by Mehta's group, which was enantioselective selective total synthesis in 14 steps from R-limonene. And the key reactions used in that synthesis was orthoester Claisen rearrangement and acid catalyzed diisoketone olefin cyclization for creating two quaternary carbon centers. Then they have also seen use Johnson Claisen rearrangement to give gamma delta unsaturated carbonyl compounds. And they have completed the total synthesis in 14 linear steps with 0.9 percentage overall yield. So this is the mechanism of Walker oxidation. So that is the formation of this methyl ketone from an alkene. So first this palladium will be converted into palladium chloride by using this copper chloride. Then again 2Cl minus will make this PdCl4, and then alkene will come and it will coordinate and replace with one of the chloride to form this intermediate. Then water molecule will attack and Cl minus will leave to form this compound. Then again, water molecule will attack over this alkene to form this intermediate. Then HCl will leave to form this kind of intermediate. Then this bond will break and this proton will shift to this palladium to form this compound. Then a 1-2 insertion reaction will take place to form this intermediate, and then reductive elimination of that methyl ketone corresponding to our alkene will be eliminated, and we will get the palladium zero back. So this is the mechanism of Walker oxidation. You can go through it, then we will proceed to the next topic. Now, the last lecture was about the synthesis of trichonanes by other reactions, where we have seen this application of Poisson-Kant reaction, vinyl cyclopropane rearrangement, aldol reaction, Nassarov cyclization, oxycop rearrangement in the total synthesis of trichonane, then application of 4 plus 4 cycloaddition in the total synthesis of coriolin by Bender and Carrera group. So this is the reaction for getting this five-membered ring, Poisson-Kant reaction, specifically to get the cyclopentene on framework. And then we have seen this. So this is the mechanism. So I am not going into the detail. You can see the steps involved in this reaction, which are alkyne insertion, CO elimination, alkene coordination, and finally, so the CO is basically coming from this CO2, CO8, and CO gas. So it is going through a series of this complex transition states, and finally we are getting the cyclopentene ring. Then we have seen this vinyl cyclopropane rearrangement, which is a ring expansion reaction converting a vinyl substituted cyclopropane ring into cyclopentene ring. So here what how it is happening: first the cyclopropane ring will cleave and that radical will form, then that can combine with either this radical to give this alkene that is known as vinyl cyclopropane rearrangement. Then we have seen this Nassarov cyclization. So a Lewis acid will coordinate with this ketone. Then this will move to here and this will come to here to form this. And then this proton will leave and this uh, alkene will form here. And then this O minus will come back and this will get quenched and we will get the cyclopentenone. So that is known as Nassarov cyclization. So this is another example. So here this AlCl3 is coordinating with this ketone. This is coming over here and this is shifting over here. Then this elimination of this proton will give the double bond and then ketoenol tautomerism will give the corresponding product. So now we will see some questions, few questions, and then we will wind up the session. So the first question is the role of copper salt as co-catalyst in the Walker process is option A, oxidation of PD0 by copper 2. Option B, oxidation of PD0 by copper 1. Option C, oxidation of PD2 by copper 1. Option D, oxidation of PD2 by copper 2. Which is the correct answer? So here the correct answer is option A, oxidation of palladium 0 by copper 2. So in the first step of the Walker process, the palladium react with this two equivalents of copper chloride to form palladium Cl2 and copper chloride. So here palladium was 0 and here it is 2. So the role of copper salt CuCl2 in the Walker process is the oxidation of palladium 0 by copper 2. Now the next question, the mechanism for the formation of molecules A and B involved respectively. So this compound is converted into this one and in the presence of H nu, and this is converted into this one in the presence of H nu and a sensitizer. So which is the reactions involved here in the both the cases. So here the correct answer is this one. So oxidipymethane rearrangement and nourish type 1 cleavage, option 3. So what is happening in the presence of H nu and sensitizer? As we have seen the mechanism, this three-membered ring will form and then again it will open up to form the cyclopropane ring. So that is oxidipymethane rearrangement. And in nourish type 1 cleavage, this alpha bond to the ketone will cleave, and this will cleave to form double bond over this position, and this will combine to form the cyclobutane ring. So that is nourish type 1 cleavage. Now the next question, the major product formed in the following reaction. So this the ketoester compound in the presence of TiCl3 and LAH, then H3O plus, which will be the product formed here. So here, this is the mechanism. Here we have seen the McMurray coupling. So this is an example for that McMurray coupling. So here radical will form, and both of this oxygen will coordinate with this titanium, and this two radical will combine. Then titanium dioxide will eliminate to form this enol ether, which will upon hydrolysis it will be converted into this alkene, and not alkene here, oxygen will be there to this ketone, so that is written as this form. So the correct answer would be option 2. So with this, today we will wind up today's session. The in the next tutorial session we will discuss some more questions, and then the week 3 assignment and the week 5 tutorial session contents as well. So I hope it's clear whatever we have discussed in today's session. If you have any doubts or you need any more explanation in any topics or any question, please do let me know. Thank you for joining, and see you for the next tutorial session. Thank you.